Yes, hello everyone. I'm Patrice Brassard from Université Laval in Quebec City, and I will chair this first session. So the speaker for this session will be Adam Ramakers, who is a senior business director at the Delica, and the title of his talk would be Delica Next Generation TCD.
Okay. Well, first of all, my name is Adam Ramakers, and I want to thank you, Professor Rickert, and the organization committee for allowing me to speak about the next generation TCD. I'm really honored, also on behalf of Delica Medical. So my name is Adam Ramakers. I started my career in the early 80s in nursing. After finalizing some additional courses, coronary care, intensive care, and burn care, I got my degree in business administration. And I worked in hospitals until 2005 as business unit manager of ICUs. 2005, I switched my career to the medical industry for sales-related position. And since just more than a year, I'm working for Delica Medical Systems. So that's my introduction, and thank you for having me on board. So the agenda of my presentation, I will shortly say something about Delica Medical, history of TCD and the basic principles of TCD, but I will do it very shortly because the audience probably knows much more about it than I do. Then I will go into detail about the next generation TCD systems, and particularly the 9F, the EMS 9M, and the EMS 9D Pro. Some of the Delica innovative solutions, the robotic probe, 3D scanning, and emboli detection. So, Shenzhen Delica Medical Equipment, the company introduction was established in 1998 by President Mr. Richard Wang, and is a national high-tech enterprise engaged in high-tech medical equipment research and development manufacturing. They are awarded several times on national level by the Ministry of Industry and Information Technology for innovative R&D capabilities, advanced technical level, high market share. Delica is listed on the National Equities Exchange and Quotations, and their stock out is A37537. They moved to the new business premises earlier this year in July 2021 with a floor area of more than 5,400 square meters or 85,000 square feet. They hold over 200 employees. National high-tech certification. They are ISO 13485, means they are allowed for manufacturing medical equipment. Of course, they have CE FDA, and Delica has 9 authorized inventions patents at the present. More than 10,000 clients internally in China mainland, including 500 territory A hospitals, and the international market share is the top 2. So, heading over to the history and the principle of transcranial Doppler, I think this is all well known by you, and how the Doppler effect was invented by Christian Doppler. But then from physics to TCD as a medical device, what a lot of people don't know maybe is that Dr. William Stein, founder of Multigen, still a US company and a collaborator of Delica, together with Robert Barnes, first used a fast Fourier transform to analyze the change in frequency of the returned audio signals of ultrasound instruments. It was done by the AngioScan, and in fact the AngioScan, that was the basis on which Roon Aastlied in 1982 found out that it was possible to send an ultrasound beam into the brain through a thinning of the skull. Well, we all know this is the TCD. The article below is in which this is described in more detail. Well, we all are familiar with this picture, the spectral display, the indices, all what's based on TCD when we're looking to the DCD, the systolic peak, the end diastolic velocity, and the mean velocity, of course. The ultrasound in tissue, it emits and receives a signal when the probe sends a signal to the blood cell. Some facts, ultrasound travels at a constant speed of 1540 meters per second in tissue. It's a reflected environment to media, and the ultrasound is backscattered in heterogeneous tissues. And as higher the ultrasound frequency, as higher the resolution, and the shallower the penetration of depth. Here you see it in sonography, ultrasound signals is used to insonate the vessels with 2 MHz. The signal is reflected and backscattered from moving objects, blood cells with a positive or negative frequency shift, as we all know. The frequency shift is also called the Doppler shift or Doppler signal. As fast as the blood cells are moving, as higher the Doppler shift. And here you see that the quotational inaccuracy and an angle of 45% will be accepted. And what you see here is, in fact, why does blood flows? Pressure is depending on compliance, compedience, and peripheral resistance. As we all know, TCD works based on pressure difference non-invasively relative to the sample volume. And by the difference in transmitting and receiving the signal, you can determine the flow speed and the direction. That is stated here in formulas. And this is for me an important slide. This is about the multi-range Doppler. The multi-range technique, the pulse wave modes at different depths. It allows 3D reconstruction of the cerebral arteries at the base of the brain. This comes back in my presentation later on. Well, in general, how to get a good spectrum quickly. It's about the amplitude, the power of the ultrasound, the gate, the sample volume, the gain, which enhances the intensity of color, which is done digitally, and it's more or less a way of photoshopping. Before the M mode show the depth of distribution of the signal and the acoustic signal. Well, talking now about Delica TCD innovative solutions, not covering other Delica solutions like multifunctional vascular ultrasound or the digital EEG systems they also provide. In this presentation, I'm talking about 3 different types of transcranial Dopplers, the EMS-9F, the EMS-9M, and the EMS-9D Pro. And on the right side, you see the application areas in which they are used: neurology, cardiovascular surgeries, neuro ICU, stroke units, research, people like you, neurovegetative studies, cardiology, and pediatrics. Going to the first system, the EMS-9F. It's a small, smart, digital, and high-quality TCD solution in a small box. You see the box over here on the screen. Do you see my cursor as well?
Yes.
Okay. Well, it's some sort of a pizza box, and it's shipped out without a PC because people buy that locally and they can put it on a trolley. And this is an examination device for intracranial and extracranial vessels because it has 1.6 and 2 MHz probes, which are especially for intracranial vessels, and the 4 MHz and the 8 MHz probes are for extracranial vessels. And we have the 1.6 because we all know that some, and especially in elderly people, sometimes it's very hard to get a good signal, and then with the 1.6, you will have more power to insonate. The 9M, this is a device, this is an ambulatory system which works for intracranial pressure, intracranial vessels, because it allows only 2 MHz probes, but monitor normal probes, handheld probes, but also the robotic probes, which I will cover later on. It is a battery powered. It's to use together with the robotic probes. It can work for 2.5 hours, and you can see you can also walk around with it. That means you can also use it as an halter. How to connect it? You can connect it by USB directly to a laptop. You can use LAN. For that, you have a very long distance, but it also can operate on Wi-Fi to a PC or to a laptop. So this means that also for physiology, if you do research in an environment on a treadmill or on a bicycle, you can use it as an ambulatory system. And then last, the EMS-9D Pro. It's an all-in-one TCD capable of connecting with the external devices such as continuous non-invasive blood pressure, end-tidal CO2, ECG, ICM. It's a light, system as well. It's about 7 kilograms, 6.4 kilograms. And this is the system which is used a lot as a multi-modal neural monitoring system, because all the connectivities you can have on this system. And for instance, you can connect it, I think the people in this audience, they know continuous non-invasive blood pressure like the company FMS or the company CN Systems. And together with ICM Plus from the Brain and Physics Lab in Cambridge, you can do multi-parameter integration. You can have the non-invasive intracranial pressure evaluation. This is of course not the gold standard because that is invasive, but it is nice for trend information. All other devices which has an analog interface or digital interface we can connect. And I know that one of the next speakers is NIRS, and I know they are working on connectivity with analog as well. So there are a lot of additional hard and software possibilities in hardware, the robotic probes, which is the main topic after this, and tidal CO2, any hardware solutions which provides analog and digital interface. Well, the 9D Pro is a multimodality solution I mentioned already, DICOM interface. Software, we are unique that we can offer peer-reviewed hits. That's the only company who has peer review hits anomaly detection available, which comes back later on. 3D scanning, the ICM Plus Cambridge Brain and Physics Lab, and integration by CSV files, Excel, or people who work with MATLAB can use it as well. Actually based on a Windows 10 platform and also in software with the DICOM. Well, and this is, I think, very important to good understand, and I think why this is very unique, what we have on the Delica TCD in our next generation TCDs. It's also tested by the group of Cambridge. You see the article below from Tyler and Smielski in Critical Ultrasound from 2018, in which they described that for a long-lasting signal for over 4 hours, it was very accurate. It's accurate, it's easy to use, save times, repeatability, and stability. But what is more important, it allows automatic temporal window finder, automatic optical MCL signal finder, and continuous tracing of the optimal signal during long-term monitoring. Here you see some examples. Some short movies behind. Here you see that it is working with the servo motor. He clicks scanning, and then you see how the robotic probe scans the area in the temporal window. And it also changes the angle. If you brief, this is very important because there's a lot of people who are used to work with TCD. It takes up from 5 to 10 minutes to find a good signal, and the robotic probe is a unique feature. This helps you to have the signal within 2 or 3 minutes. Now we scan the complete area, and then you see their part is green, and okay, we'll go to the next one. This is the scan function. This function allows automatically to perform a general scan of the window. In order to find the signal you're looking for, the feature allows you to choose from higher intensity, best signal, or highest velocity. And that's particularly important in clinical settings like stenosis and vasospasm. You can also select the angle scan, and the software can also change automatically a bit the depth in order to take a better signal. If you have multiple points with signals, you can click with the mouse the one you prefer. You see the green dots on the screen, and you can click, and also you will search in that area automatically. Then we go to the search function. Once you found the signal and scan, you can press search. It performs a high resolution search in the surrounding areas. And the best signal you may have in a relationship to the window, where you put a probe and the other parameters you select, the depth, the gain, and the gates. No, come on. Yes, here you see the search function. And you can hear, if you press the search, it performs a high resolution search in the surrounding areas. That's what I mentioned in the previous one. So the robotic probe can scan the complete area, or with the search function, you can find it on a point you are working. Let's see. Now. This is about stability. We all know that sometimes when patients or subjects are moving their head, it is very easy to lose the signal. And here on this video, you saw that it is very stable, very rigid, and it's very hard also because of the headband of the robotic probe is very firm and very well positioned on the head. And this last short video about the robotic probe is about the bilateral function. Once you found the signal on the first channel, you can check the second channel, and following the same steps, you may find very quickly the signal on the other side. What normally takes 5 to 10 minutes, this is done within 1 to 2 minutes. Well, going to the other innovative solutions, I said earlier in this presentation about the way we can, with pulse wave, we can go in depth. It's with 3D software available on the EMIS 9D Pro. You see here on the left-hand side, you see the difference depth, and here you see a picture of an image which is calculated mathematically by using the 3D scanning. And sorry, I have a little movie again, and I will turn off the music of this one. Go to very slow, very. So heading over from the movies, this is in the past now. My last topic about the innovative solutions is about peer-reviewed embryo detection software, and also the article which I refer to is mentioned below in this article. This EDS is peer-reviewed, certified embryo detection software with a built-in artificial intelligence, which allows rapid diagnosis of solid embryo in long-term time series. And here you see its high-intensity transits and two examples of embryo, a single solid gaseous embryo, which you can see on the picture here below. It's zero crossing line, very stable, it's very frequent. You see the embryos over here, and here you see a gaseous which moves around the vessel completely. And on the other side, you see two kinds of artifacts, movement artifacts, which has a completely different pattern, and also a speech artifact. Of course, there are also other artifacts. Think about, especially during surgery, when diatomy is used. Well, this is about some unique features I think Delica has to offer, and which makes us the next generation of transcranial Doppler. Our values are customer-oriented, close collaboration, practical, open-minded, and enterprising, which are also to mention the goals of the company. More innovative solutions are on the roadmap, which cannot be disclosed right now at the moment, but please follow us on LinkedIn and Twitter for our future developments. So, thank you all for your attention, and any questions, please feel free. And I'm just exactly in the time, I think.
Thank you very much. Yes. So we already have a few questions, so the discussion period should be interesting. So the first question from Rani Panray: can the EMS 9M accept other signals to be combined with cerebral blood flow velocity, for example, ECG or phonometer output? So the EMS 9M.
That's a very good question. No, it cannot, like the EMS 9D, it cannot incorporate the signals, but of course you can extract the data, and if you have your CSV files, and what I know that most of you people are working with other systems, so some sort of data acquisition systems, and if you work with CSV, Excel, or there are a lot of MATLAB experts, I think you can combine it, but you cannot feed in the signals into the EMS 9M, if that's the question.
Okay, thanks. Second question from Dr. Panray, and I also have that the same. Does the robotic probe work well with the PCA?
With the PCA, what's mean with the PCA?
The posterior cerebral artery, because you focused on the middle cerebral artery.
Yeah, but yes, that's good. But you saw also in the picture, it shows in depth, so you see the different depths. But never forget that TCD was mainly developed for the MCA, but because of the we can make a picture build up from the different layers inside the brain.
So it works with PC as well.
Depends on the depth and the parameters. So yes, you can you can search for it.
Okay, and a follow-up question from Shek Sang: what about the ACA, the anterior cerebral artery?
Well, it's also, of course, the robotic probes are here. So but I think that's the I think the answer is the same. If you look for it and you find a signal, you can do it. And building up this 3D image, because you saw it was speeded up in this short movie, but normally it will take about 3 to 4 minutes, but you can do it several times during a measurement, of course.
Okay. Mm-hmm.
And it just and to find it, you can just put the probe a bit forward in the window, and then and you will find it.
Okay, thanks. Carolyn Rickards, I have a question as well. Oh, sorry. Do you have to identify the desired depth, or does the system also adjust for this automatically?
Oh, that's a very good question. Well, what it does, it finds the highest velocity or the best signal, or so that it does, and you can choose for either of them. And then, depending on which vessel you're looking to, but normally it will find for the it desires depth as a start, but the system adjusts later on.
Mm-hmm. Okay. Next question from AJ Rosenberg. Thank you very much for your presentation. Does the EMS9F have 2 analog output channels? And what is the appropriate cost of the EMS9F system with probes and software?
That's a very good question, but the cost it's an easy question. It's depending on which territory. I only are familiar with transfer prices, and of course we have global partners, and global partners they are depending on their local rules, the local cost. So I don't know what end user prices are in different territories.
And does the EMS9F have 2 analog output channels?
8.
Okay. Next question, Thomas Vincent. Do you have other more lightweight caps that would allow placement of other devices like NIRS or in the context of cranial surgery?
So please ask that question again, please.
Yeah, sorry. Do you have other more lightweight caps that would allow a placement of other devices or in the context of cranial surgery?
Yeah, and what other devices? What's meant by other devices? Well, for intracranial surgery, what I mentioned, people use 60 megahertz probes, and they are sterile as well. But I'm not sure what is meant by other devices or small caps. The robotic probes are as they are, and I know that well, they're not that bulky. They're good, and they stay fit.
Okay, is it, yeah, Thomas, maybe you could open your microphone and complete the question if, or not. Okay, we'll follow up to the next question. Maybe a last one. Alvar Gulbrandsen, thank you for the presentation. Does the robot only use pulse wave mode? And if so, what is the range of thermal index, usually during scan period?
That is a very good question, and I must say I'm not sure if I can have this question and by email. I will answer it. And this is a technical question. I cannot answer at the moment. Okay.
Maybe a last one for me. Is it possible for the robotic probe to at some point lose the signal in the middle of an experiment? And if so, is it possible, or how the machine will react at some point if we are losing the signal?
Well, that's a good question. In fact, when you saw it when my colleague on the movie, he changed it, he moved the probe a little bit. With this function, he will automatically go back to the lost signal, and he will find the signal for you again. So, and that's we noticed this, that sometimes it's this could be a problem during carotid surgery when the surgeon is moving over and putting, but you have to put a lot of force on it. But then if you just put it back a little bit, it will auto search again for the best signal.
Okay, thank you very much, Mr. Ramakers. So I think Caroline will move on to the next session. Thank you again.
One last remark, that is called what I mentioned, the track function, and we can choose the percentage of loss of signal, and then it will automatically find it again, and you can put it in 15 or 30% loss of the signal, and then it will auto track the signal again.
Okay.
All right. Thank you all. Thank you for having me on board.
Thank you.
Thank you.